Normally when you do a titration, you stop when the indicator changes color, but we're going to go well beyond that. We're going to stop when the pH flattens out. And so when the indicator changes color, the pH is still skyrocketing up, and then we'll just keep adding until we don't really see much of a change occur. And so what that means is this: we're going to monitor the pH continuously with milliliters of sodium hydroxide. The sodium hydroxide will be our titrant solution here. And it depends. We'll have two unknown acids. We have, well, two categories of unknown acids. The first one is you might have a monoprotic acid. If you have a monoprotic acid, then what happens with the pH is it starts off lower here, and then it goes up a little bit and flattens out. And then there's a steep rise in the pH, and then it flattens out again. This steep rise in the pH at the inflection point here, this is what we call the end point. Or actually it's not really the end point. At the point of inflection here, right in the center, that's called our equivalence point. That's called our equivalence point. The actual end point of the titration where the indicator changes color, and the end point is like about here. This is the end point with phenolphthalein. And you want the end point and the equivalence point to be the same, but because of the indicators that we have, these are just colored dyes. Sometimes they're an error, and the amount of error is usually like a drop, maybe less than a drop. And so this is more vertical. I didn't draw it quite vertical enough. So there's very little error. Hopefully there's very little error. You know, it depends on what indicator you use. But our indicator that we're using is phenolphthalein here. But this is what we call a systematic error. All our titrations are going to have this systematic error. It's just going to be a little bit off, you know. But if it's systematic, we do a calibration first, you know, like a standardization calibration first, and then those are all going to be off. And even if we didn't correct for that by doing the calibration, the error is still very small. You know, the difference between the equivalence point and the end point in terms of milliliters of sodium hydroxide. In terms of pH, the error is quite a bit more significant. Depends on the, for example, a strong acid, strong base like HCl, sodium chloride, sodium hydroxide, there would be more significant. But a weak acid, there's less of an error there. And so what we're going to do is we're going to take data. But each reading of the pH, so let's say you add a drop, you have to wait until it mixes and the pH stabilizes and then take a reading. How many minutes does that take usually? It takes like a minute or so. We're going to go out to about 50 milliliters, you know, 45 to 50 milliliters here. There's roughly about 20 drops per milliliter. And so this gives us up to, if we did all 50 milliliters, that would give us about 1,000 drops, or what is that, 100? 20 times 50 would be 1,000 drops. And if you take about a minute for each reading, that would be about 1,000 minutes. 1 minute per reading is like you have to add the drop and then let it stir and then make sure that the pH stabilizes, right? And that would be 1,000 minutes. But the problem is, do we have 1,000 minutes today? We don't have 1,000 minutes. It's going to be impossible to do this drop by drop. And so what we have to do is we have to sacrifice some data. So what we're going to do is we're going to take it at larger intervals at the beginning. So we'll take an initial pH with 0 milliliters, and then we're going to just take pH readings at every 1 milliliter. So otherwise, we're not going to finish this. And so we'll go to 2 milliliters. That's okay if the pH doesn't change much. Then we go to 3 milliliters. And so we go to 1 milliliter intervals. However, when we go here, if we go with a 1 milliliter interval near the equivalence point, what's going to happen is we're going to miss it. We're going to miss where the rise goes. Did the rise occur? Where did it occur in that 1 milliliter interval? We need to pinpoint that to the nearest drop. And so what we're going to do here is we're going to, you'll notice the pH start to rise. As the pH starts to rise, slow down. You know, we're going to go to half a milliliter or even drop by drop. When you're near the equivalence point, you need to go drop by drop. And so in this range, we should go drop by drop. Because I told you it's very steep. It's steeper than what I have drawn here. So it only takes about 3 drops or 4 drops to traverse this entire rise. And if we miss it, then we're missing a crucial piece of data. That is the titration curve at the equivalence point. And so we have to be very careful here with our data collection, because if we go 1 milliliter, 1 milliliter, 1 milliliter, then we might not quite get this here. And we need to map it out. How steep was it, etc. And so what we have to do is keep an eye on the pH, and as you start to see the pH rise, we need to start increasing our data collection, that is decreasing the intervals. So we'll go drop by drop, and then once it flattens out, then we'll increase the interval again here, decrease the amount of data we're collecting. And so in other words, we can live with lower resolution data here, but in this region here, we need higher resolution data. That is, we need to collect a lot of data so we can see the fine details of the structure here. But this is like going blind. You know, when do you know you're going to hit it? It's like that. There's that board game Battleship, you know, where you're just firing shots trying to see where it is, and the same thing happens with this. And so what we're going to do first to help us is we're going to do a trial titration. The trial titration is to figure out 2 things. One, we want the optimum sample size. And 2, to determine the where the equivalence point should be. I'm just going to say estimate, because where the equivalence point is. So the first thing is, how much unknown do you use? So our unknowns are solids, acids. These are large organic carboxylic acids. And so we're going to weigh these in the Chem 1A analytical balance. So what you're going to do is you're going to weigh, let's say, 0.1 gram sample or something like that. What, in the procedure, how much does it say to weigh? 0.1 grams. But what you want to do is you want to weigh 0.1 xxx grams. So the balances we have here aren't precise enough. We only have a tenth of a gram, or actually a hundredth of a gram, centigram balances. So don't use the Chem 1B balances. They're not precise enough. What we need to do is we need to go to the Chem 1A balance, which weighs to the tenth of a milligram. So these are tenth of a milligram balances. And then we're going to run a regular titration. A regular titration is just with phenolphthalein. And here we're not going to measure the pH as we go along. What we're going to do is we're just going to hit this to the end point. That is when it goes from colorless to pink. How long does the pink color have to persist for? When you run this, you want to get it within a drop or half a drop. And so it's going to go from colorless. And then what we want is we want to just add like 1/2 to 1 drop. And then it should go to what color? It should go to pink. It's not the shade of pink. It's that we need to go from colorless to pink within 1 or 1/2 drop, and the pink color needs to persist for how long? It's got to stay pink for like 20 seconds or so. If it, yeah, with swirling, it should stay pink. It's not going to stay pink for for very long after that because of CO2 in the air. So try not to breathe out on these. And so we're going to do this in a regular Erlenmeyer and then swirl. So stay pink for 20 seconds with swirling. If it fades and goes back to colorless, no problem. We'll just call that endpoint. All right, and so our target for the equivalence point, what we'd like to do is we'd like to have the equivalence point come in at about 35 milliliters here. And so ideally, if we could make this at 35 milliliters, then we need to slow down before 35 milliliters comes. Maybe a milliliter, like 34 or 33.5 milliliters, we start to slow down. I mean, this really, I drew way too many dots in here, but really it's only defined by about 2 or 3, maybe 4 dots. It rises so steeply that it's easy to miss. And so in case your trial titration wasn't so precise, we need to err on the side of caution. And so let's say your target was 35, but you start to notice some pH increasing at around 33, then I would think that you better start to slow down. Maybe go 0.5 milliliter, even though it's well below 35, just to be on the safe side, because you don't want to miss it. Other people, they go drop by drop and nothing's happening. And it turned out to be later, so they kind of get tired and then they go, well, nothing really happened. And so they increase the interval and then they miss it entirely because it came at 36 rather than 35, you know. And so just be careful of that. And so you're going to use 2 things. You're going to use your trial titration data, but in case your trial titration didn't go so well, you're going to keep an eye on the pH and make sure you don't miss it. All right. And so what we're going to do is we're going to calculate the optimum. So what we're going to do is we're going to titrate this. We're going to get the milliliters. Okay, so you're going to have your 0.1xxx grams over, however many milliliters. So there's going to be xx.xx milliliters here. And then our optimum sample size is going to be for 35 milliliters. So we're going to calculate Z grams, this is optimum, to titrate to 35 milliliters. Right on. And so get as many digits, and then we're going to weigh this amount on the balances there. If you overshoot it a little bit, it's not a big deal. If you overshoot a little bit, then you just have to figure out where your equivalence point is going to come. You can just do a quick calculation here. And so it doesn't have to be right on. Don't spend an hour trying to get it right on. You know, it could be a little less or a little bit more, but you should get it to Z grams. You know, whenever we're doing titrations, it's all quantitative, so we try to get as precise of data as possible, so as many sig figs as possible. And so this is right on 35. I mean, it should be exactly 35, hopefully. Okay, then we're going to run the titration. Okay, so with that optimum sample size, we should get a curve that looks like this for monoprotic acid. Your unknown acid could be diprotic. In Chem 1A, you were told, you know, if it was monoprotic or diprotic. In Chem 1B, we could figure it out ourselves from the shape of the titration curve. So diprotic acid will look pretty similar, except it's going to have two rises here. And so the first thing is we need to make your unknown as concentrated as possible. So the, you know, instructions like this are made for any acid, any unknown acid, you know. But when we're doing this in practice, you know, like for example, the least soluble acid, they'll write the unknown, you know, how much water you need to add. But what you're going to do is you're going to dissolve, this is important here, dissolve, it doesn't matter if it's monoprotic or diprotic, but for your pH titrations, oops. So what we're going to do is we're going to try to dissolve our unknown acid in a minimum of DI water. So a minimum means it's going to be the most concentrated possible. The most concentrated possible is going to give you the lowest pH. If you use too much water, let's say you keep diluting it and keep diluting it, what pH will it converge to? If you keep diluting your unknown acid, eventually it's going to be so diluted it's like pure water. Pure water's pH is pH 7. So by adding more and more water, what happens is the pH of your unknown goes up and up and up. If your pH of your unknown goes too high, then what you're going to do is you're going to miss the first wave. You need to start off as low of a pH as possible to catch the first wave. The first wave is small. The second wave is big. So this is the behavior of pH. The first wave is what we call the first equivalence point. First equivalence point. And the second wave is going to be the second equivalence point. So what happens is people end up diluting it too much. They add too much water and they barely get a ripple for the first wave. And so it's happened in the past where people think they have a monoprotic acid but they just missed it. You know, they see a little ripple and they think nothing of it. It is going to be a little ripple here. But if you did your titration correctly, then what we're going to have is this, the second equivalence point should come at 35 milliliters. Because if we have a diprotic, phenolphthalein, because of the pH, it changes that, will only catch the second. The first equivalence point is invisible to phenolphthalein. It happens in the colorless region of phenolphthalein. And so we don't know if we have a monoprotic or diprotic. So regardless of whether you have a mono or diprotic, what we're going to do is we're going to go to half of 35. Half of 35 is 17 and a half. So around 17 and a half, we're going to start collecting extra data here to see if we get a little wave here. You might not. It might stay flat, or you might have a little bump. But we're looking for a little bump here. And so around 17 and a half, before you hit 17 and a half, not at 17 and a half, 17 and a half is the middle of the wave. We need to catch the wave at the beginning and at the end. You know, so many people, I don't know why, so many people stop the pH titration once they hit the end point, you know, when phenol changes color, and they miss this entire back half of the titration. We can't stop there. So we need to catch the wave at the beginning, like before 17, and we need to catch it way at the end. The same thing with the second wave. We're going to catch this, and then we're going to make sure there's nothing else happening. So we're going to titrate this out to about 50 milliliters, going at 1 milliliter intervals. So we're going to collect the whole spectrum of data here. Okay, so hopefully the Terral titration is pretty important. Hopefully that goes well, that, you know, it's right on 35, but it's hard. It's hard because for some of you, you know, we have to think about relative error. Why do we want so many milliliters here? You know, and so when we think about relative error, the trial titration is going to have a relatively high error, potentially. It depends on how many milliliters it takes. For some people's trial titration, it only takes like 5 milliliters. If it only takes 5 milliliters versus another group's trial titration, which takes 25 milliliters, there's a huge difference in relative error. So for example, let's talk about relative error in titrations. We want to use the most titrant possible. You know, we'd like to use the most titrant possible because let's say a 1 drop error in 5 milliliters versus a 1 drop error in 35 milliliters. There's a big difference. So if you only have 5 milliliters, that's 100 drops. So 1 drop in 100 drops is like a 1% error. Okay, 1% error. But 1 drop in 35 milliliters, that's 20 times 35 would be 700 drops. So if you have 700 drops and you have a 1 drop error, is that a big deal? Not as big of a deal as 1 drop error in 100 drops. Does that make sense? So the more volume we have, the less, because our titration could have 1 drop error, you know, or maybe more depending on your titration technique. Hopefully not more. Maybe like a half a drop. A half a drop is even better. It'd be half the error. And so this is a much smaller error here. This is a much larger error here in terms of relative error. And so when we do our titrations, like in Chem 1A and Chem 4, I see a titration and they really screwed up and they used like, or in Chem 1A, not Chem 4. Chem 4 they can't screw it up. In Chem 1A they weigh the wrong sample size and they're doing a titration with 4. They hit the end point at 4 milliliters. You know, 4 milliliters is not good. You know. All right, so what we're going to do is we're going to check out the equipment and then we're going to run our trial titration. Unlike Chem 1A, we're not going to standardize the sodium hydroxide. The stockroom has already standardized the sodium hydroxide. And so you could write this down here. The sodium hydroxide that we're using has a concentration of 0.1107 molar. Sodium hydroxide, standard. The solution. So we just want to collect the data today and then we'll analyze the data later. All right, now when we do the pH titration, what we're going to do is we're going to use a beaker. Normally we don't like to use beakers for titrations because splattering is, much easier in a beaker. Like this could splatter out and we'll lose it, whereas in Erlenmeyer we're a lot safer from splattering. And so what we're going to do is we're going to dissolve our unknown acid in a minimum of water here, like this. And then what we're going to do is we're going to put a magnet in here, a magnetic bar. And this is a Teflon coated magnet. It's called a magnetic stir bar. And then we're going to place this on the stirrer. But the trick is, I told you to dissolve it in a minimum of water, but we have to submerge the probe completely. And so the glass bulb here must be completely submerged. So let's say you're very good and you dissolved it in a minimum, but you didn't submerge the probe. Unfortunately, we have to add more water. You have to add more water until the bulb is completely submerged. And then usually what I do is I just clamp the pH probe here. And so you'll have to adjust everything. And then we need the stirrer bar to be in the center of the stirrer unit. And so I'll just move the stirrer unit until it's centered here. And then there's an RPM and a heat. We're not going to touch the heat. We're going to change the RPM on this. So adjust the RPM so that we stir it without splattering. We don't want any splattering. So try to get the maximum stir rate without risk of losing any solution out of the beaker. And then you'll adjust it so that the pipette, these pipettes are very expensive. They're $200 pre-COVID. So post-COVID and inflation, they're probably like $400, I don't know, $300 now. So be careful with these, don't break it. And then we're going to record the pH initial, with 0 milliliters of titrant, and then we're going to go to 1 milliliter intervals, and then we're going to go drop by drop intervals. Each time you add, you have to wait until the pH stabilizes, which is painful. Okay? Takes time. But it's easy, I think. And along the way, you want to visualize the curve, You want to make sure you got enough data to properly sketch out the entire curve in your mind. Okay. All right. Any questions on this? Just collecting data. All right. That's all I'm going to say then.